All right. Now half the class is out today with strep, I think. So we're gonna go ahead and start. Um so we've got like this picture looks kind of like this. You've got a rod along the x-axis, got length L. Right here, the rod has charge density lambda. Okay. So you take a typical increment of length delta L at position I like to use x star somewhere between 0 and L. Okay, so x equals 0 here. X equals x star here. And this point has some coordinate. And I forget what that is in your text. We could, you know, Zoom has the obnoxious characteristic that if you hit alternate tab to change windows, it suddenly doesn't want to do that. Because the alternate key switches displays in Zoom. So it does that, but it doesn't change windows. So you got to go to the mouse. That's not terrible. I can get used to that. Okay. Okay, the one thing that I didn't remember is this point is a distance A. The end of the rod. Okay, so what's happening is every point on the rod, every charge on the rod is exerting, well, it creates an electric field at this point. Okay. And the charge is equally distributed, so the parts of the rod further away are clearly going to contribute less electric field than the ones that are closer. Okay. And how are you going to deal with that? Well, you're going to do an interval. You want to sum up what the effects of all the charges on the rod are. So what you do is you take a typical increment. That's always what you do when you set up an interval. In this course, it looks okay. You take a typical increment and see what effect the charge in that increment has at this point. So you take a typical increment, delta L, at position that I'll call x star. That's an asterisk. It's asterisk, it's easier to say x star. So when I say at x equals x star, I mean where x star is some x coordinate within the interval. Okay, so I'm abusing language a little bit by saying at x equals x star. I could say around x equals x star, but at is a shorter word, takes less time to write it, it takes less time to say it. So I'm going to use at. Okay, and you'll hear that. You know, it's not quite precisely correct, but everybody knows what it means. And now you do too. Okay, so increment delta L at x equals x star. What do we know about it? And I'm going to call this point P. I'm not going to go back and look at the statement of the problem, see what the book calls it. Okay, it's a point P. Increment delta L at x equals x star. The distance from P is clearly L plus A minus X. Because the coordinate of this is, of course, we could label a lot of things. X equals L here is the end of this thing whose length is L, and one end is at x equals 0. Okay, and here x equals L plus A for obvious reason. R is lambda delta L. The field at P is Q over R squared. It's obviously times the I vector, because your R vector would go from here to here in the I direction, and then you would divide that by the magnitude of the R vector, and the R vector from here to here divided by its magnitude is obviously I. Now, if the charge is positive, that's going to give you an electric field in this direction. If the charge is negative, of course, then KQ over R squared is going to be negative. You're going to have a negative multiple. I have electric field to the left. Now, what's Q? It's K lambda delta L. What's R? It's distance from the increment to the point P, which is going to be this distance. So there it is. This leaves the integral is the sum of K lambda delta L over L plus A minus X quantity squared times I. You could put subscripts, and there should be an X asterisk here, an X star. Put an I on your X. You could put an I on your delta L to indicate that you've maybe got N intervals, and this is the ith one. And that should be totally familiar to you from calculus. And this then approaches the integral from 0 to L, because the delta L go from 0 to L. Okay, the increments that you're looking at that create the field at this point go from 0 to L. And I'm going to change one thing in my notation. I called this a delta L at the beginning and then stuck with it. And really, I want to call this delta X. Makes the notation clearer when I get to here. So just going to change all the delta L's to delta X's. And I think that's all we got, delta X. See any other delta L's? So their delta X is up here. When you wave your hands over these things without doing the formalities of the Riemann sum, your delta X has become your dx's. And you should understand, you should understand it's a deep theoretical level, at least at the theoretical level, it's a level of the calculus course, how this sum works. Okay, so then I could say that equals the integral from 0 to L of this constant goes out in front. It's going to be 1 over minus x quantity squared dx. There's your interval. Okay. Then use whatever integration. And you just got to do u substitution. Of course, I use u here instead of I'm trying to think of a good letter to use here. Can't use A. Usually U and V and W and stuff are good things. I'm just going to make it an S. So we're just going to let S equal L plus A. Round that off a little more stuff. It looks much more fun. That's an S. You're going to substitute this. You're going to integrate. You let U equal S minus X. Du equals negative dx, etc. Okay. And I'm not going to do the integration. That's just a first semester calculus substitution. You're going to integrate negative 1 over u squared. You're going to get 1 over u. Then you go X. That process makes sense? Should. Now, that was one of the two problems in a pair. The other problem in a pair had a line of charge here. Up here. Well, that's how. You sure you can do those problems? Just ask yourself what happens. What's the effect of a typical increment? Okay, that's all we did here. And you look even told in the problem itself. Now you take a typical delta X or delta L or whatever it is, multiply that by lambda, there's your charge. Now, what effect does this charge have at this point? And now, what's your interval? Okay, they broke it down for you. I think in the second problem in the pair, they didn't break it down, but you could use exactly the same instructions. Those instructions are exactly what you do to set up integrals of this nature. Okay. Of course, some of you have multivariable calculus, set up integrals in higher dimensions. It's pretty much the same stuff, but it looks a little different. Okay, so let's be clear. There was one question of why is that minus X? Well, actually, it should have been minus X star. Okay. And I use minus x star down here. I did here. So let's be clear. The position here is x star. The distance from here to here is the distance from here to here minus the distance from here to here. So this is this minus this. Okay. And this is L plus A, and this is X star, okay, which became X when we did the Riemann sum thing, which we waved our hands over. Okay, as physicists and engineers typically do, sometimes to their great disadvantage, but often they get away with it. And they, if they're any good, they learn when they can get away with it, and they know they can go back to the fundamental principles. Okay. Now, most physicists are good because most physicists have doctorates that have analyzed everything very thoroughly. Most engineers have undergraduate degrees and haven't totally understood all the details of the calculus, theoretical details. Just most engineers gravitate because of time pressures and all kinds of other things. And most engineers don't learn quickly enough to incorporate it all completely. Some do. So just watch out for them. Okay. You have the potential to do it if you have time. But it takes to do it. Now, that leads me to just a comment. And I'm not an engineer, but went to a school where engineering was the big thing. Okay. It was all science and engineering, mathematical sciences. So I don't claim any authority, but I often wonder, since engineers ultimately, 90% of them end up just using software, where does understanding this fit? Okay. Well, in multivariable calculus class yesterday, one of the students said, well, what he hears from engineers is you don't use this stuff, but you use the problem solving skills you get in learning your physics and your math, and then you apply it to these engineering systems. And I would echo that. And he says this is what he hears from engineers, okay, practicing engineers. I'd go further and say that if you really want to understand the system, you've got to understand these details. Okay. And if you're an engineer and you're dealing with a system and you don't have this conceptual framework, then you're limited in the way you can design things, the way you can analyze things, the way you can troubleshoot things, depending on what you're doing as an engineer. I think. And my grandson is in his second year as an engineer, power systems engineer, and I'll be picking his brain because he's had some of my courses. Okay, he's had this course. No, actually, he's had the physics. He didn't have this because he had to do some stuff while he was still in high school. So I'll be getting his perspective on this too. Interesting question. Now let's move on and talk about the physics of capacitors, capacitance. So here's just kind of a schematic of a parallel plate capacitor with charge density of sigma. Total charge is sigma A. plate area A. Then by Gauss's law, we get the electric field. And I'm not going to talk about the details of that. I've talked about that several times. And it's in the transition problems. You got to know it. You got to test them in the next few days. Okay. Testing you on the rest of it. But your background should have this lot. Okay. There's your model. So what's the capacitance? Capacitance is the amount of charge you contain per volt of potential difference. So can you tell me what the capacitance of this capacitor is? Okay, now it's something you know perfectly well that you're missing, but what I'm hearing is, okay, let's see, total charge is sigma A. Well, I wrote that down, but I think you figured that out. So that's your charge. And now the question is, what's your potential difference? Okay. Well, in context, remember when we had a wire potential difference, the length, how do we get the electric field? Well, the field, well, voltage is, okay, what's voltage? Let's just, you need to have this reasoning firmly in place in order to understand everything well. Okay. What's potential difference? What are the units? You know, it's joules per coulomb, which tells you it's work over charge, right? Okay. So voltage is force times delta S over Q, which could be back too far, which would be QE delta S over Q, which is E delta S. Does that help? What's potential difference there? Okay, so potential difference is by analogy with this that you should be very familiar with, because what we did with circuits last month, okay, in lab and so forth, you know, all the reasoning and the units and everything that the transition problems should have as firmly as possible in your brain as it could be. Tells you very quickly that the voltage is equal to the electric field times the separation. Okay. That's the capacitance. Now, there are other kinds of capacitors. depicts the splitter capacitor. Inner radius big R. Get the length up. Let's say we've separated charge Q, meaning we have plus Q on the outer and minus Q on the inner. What's the potential difference? Now, I'm not going to drag that out of you because that requires a couple steps. Thinking, what can you determine from these charges using Gauss's law? Okay, well, by analogy, what you needed to know to find the potential difference here was the electric field and then separation, right? Okay. So can you tell me what the electric field is between these two? They're not plates anymore. They've been all rolled up in the cylinders, right? And one of them smaller than them. But we can hook up circuitry. We attach a wire here to a source and then run it to here and separate charge, right? We can pull negative charges off of the outer and deposit them on the inner so that we have a plus Q outer and negative Q inner. So I want to look just N on here. Okay, so we've got little R. Okay, that's pretty good. So better than I usually. Okay, we got little r, we got big R. Okay. Now, what's the obvious Gaussian surface that we're going to use to determine the electric field at a point between these two cylinders? So I got a point here. I want to know what the electric field is at this point. And of course, again, this point in this cross section is somewhere inside. It's not at the very edge, because at the very edges, field gets a little funky. Okay. Then assuming it's much longer than it is around, you know, its length is much greater than any of the radii or diameters, we can kind of ignore the edge effect. But this is somewhere away from the position, the cross sections where the edge effect would be significant. Okay. And we assume that's so over most of the atmosphere. Okay, so at this point, what do you need to know and how do you use Gauss's law to figure out the electric field? And I'm trying to pause this thing and it's not doing it. Okay, now you really would expect you would know about the Gaussian surface that you use for long straight wire. And you use that for any cylindrical distribution. We put the cylinder around the wire. We did this in class. I had this up front of the screen. And, you know, the wires comes out the center of the cylinder, if I get that to happen without plugging the picture, but cylinder symmetric around the wire. If we know the charge density on the wire and the length of the cylinder, we can figure out the flux. We can figure out how much charge there is enclosed in the cylinder. And then the flux is 4 pi kq. Okay. And then we divide that by the surface area of the curved part of the cylinder, and we get the electric field using all the symmetry and everything. I want to review that because we did that in class. Okay. Or could be I did it in lab, but I'm pretty sure I did it in class. Okay. And then you really have to understand that problem 22 and set 1. And also problem 23, the Gaussian surfaces that you use. Remember the other day when I had this thing over a plane, talking about the Gaussian surface, it tells us how you reason this out. The two fields that reinforce in between, you cancel outside, and all that. You really need to know all that for this chapter. Okay, so what you do is you do a cylinder in between these two. These are concentric cylinders. It's implicit that they're eccentric, but at least state that. Okay, so we're going to do a cylinder between these two. So this represents a cylinder between the inner and the outer. What's the flux? Okay, so the basic principle of Gauss's law is that the flux through any surface is equal to 4 pi k times the charge enclosed by that surface. If we have a cylinder here, it encloses charge negative q because it's around the inner cylinder, which has charge negative q. Okay. So the flux is, be careful, negative 4 pi kq. And what's the flux? It's the area times the electric field. Now it's technically it's the area times the component of the electric field perpendicular to that surface element. But by the symmetry, the electric field is radial from the axis. So the area of that cylinder is length times circumference. Remember, you talked about unrolling the piece of paper. Okay, you unroll a cylinder, and the circumference becomes the length of a rectangle, and the width is the length of the cylinder. Okay, so that's R times L. Simple. So what's E? It's 4 pi k cubed negative over pi RL, which then equals negative 2q over L. What's wrong with the units? Oh yeah, 2k. Never mind. Looking at the symbols with that A and not thinking about what I'm doing. It's kq over Well, S tree and K and R, it's the same symbol, so I just take all this off. And then the units didn't work and nothing made sense. So I took a closer look at what I did. Remember, you need to be thinking about whether things make sense or not. When you make stupid little errors like I do all the time, you learn to check yourself as you go. Okay. So this has units of K times charge over length squared. This is a length, this is a length. That's like squared times coulombs over meters times meters. Okay. Meters squared. Divide out and you get units of charge, newtons per coulomb. Okay. Field. Okay, so there's the electric field. And it's radial. So how do you get the potential difference? Yeah. Oh, here's a picture now. Here's our inner. There's our outer. In between here, we have an electric field. Now, the electric field turns out to be in this direction. It's stronger as we go from the outer to the inner. So I'm kind of indicating it that way. So, well, we can think of, if we want to get the potential difference, some path to outer. Now, what's the path from inner to outer? Well, I'm going to have to leave it to you to pull this out of the book and read it. Okay? This sets it up. And then you get a very easy integral. And, you know, we've taken too much time with this because it took a long time to get to the whole idea of a Gaussian surface. Okay? So hopefully you would have been a little better prepared for those couple of problems at the end of set one in the transition set, over which we have a test in the next few days. But take what you get there. I would start by taking a good look at those transition problems, read the chapter, and see how this works out. You're going to need it. Okay. Now you could also have a spherical capacitor. And you're going to have to read that. Your book has really good pictures. If you understand what I've done so far, it's not going to be difficult for you. Okay, but we got to move on. Okay, so we got to talk now about the energy in a capacitor and energy density. So whatever capacitor we have, whether it's this simple basic parallel plate capacitor, a cylindrical capacitor, a spherical capacitor, and that's all you have to worry about in this course. Because I don't know how that molecular level capacitor works anyway in our particles. So, there's a lot I don't know, but these things are pretty straightforward. Okay. Um, so now we're going to have capacitors in a circuit, some kind of a source. Here's a capacitor. Here's our voltage with a switch. Close the switch, the capacitor starts charging. And this is all addressed up to the point of an integral in the transition problem. Close the switch. Close, charging capacitor. So QC, which is a charge on the capacitor, equals what? Well, the capacitance is Q over V. So the charge of the capacitor is going to be C times V. And let me back up something a minute. Okay. The voltage across the capacitor is the charge of the capacitor divided by the capacitance. look like coherent. The energy required to transfer charge delta Q is just VC delta Q, which is QC delta Q over C. Abbreviating this a little more than I should, but the idea is that if you sum up the energy transfers, I'll call this a delta W, because I don't have a better symbol for it. This understanding leads you to this interval, and it's not Q over V, it's Q over C. So without going into more detail, the idea is you multiply voltage across capacitor by the charge you're transferring. So you're actually doing the interval it's a good place to work this in, but you're doing the integral of voltage across capacitor times delta Q. That means you're integrating this, and you're going to get Q squared over 2C. Now that's developed pretty well conceptually in the transition problems. Make sure you pay attention to anything in the transition problems that involves capacitors, okay? And you can read it in the book. It's not difficult. It just comes down to the idea that this is undeniably the work you do. Multiply the voltage by the charge transfer, get the energy. And the voltage is charge of the capacitor divided the capacitance. That's your word. You integrate it, and you get the energy of a capacitor. It's a simple integral, and you shouldn't have much trouble with it. Okay, so integrating the work that's required to move charge onto this capacitor doesn't depend on the resistance. You got to charge Q in the capacitor. You got to integrate Q over C, which is the voltage times the increment of charge. Okay? Just comes down to this. That's the energy stored in capacitor charge Q to capacitance C. Question is, if we have this parallel plate capacitor over here, these dimensions, what's the energy density? No, it doesn't matter whether we think of a parallel plate capacitor or another. It's the energy per unit of volume. What's the energy stored in this capacitor? when the charge density is sigma, it's Q squared over 2C. Now, here's your capacitance. Q is just sigma A. This would be among other things for this model, 4 pi k sigma divided by the volume. What's a volume? This field exists in. Okay, now got that very quickly. Four pi k sigma over A times D. Uh-oh. 4 pi k sigma is not 4. It's squared over 2C divided by A times D. Well, we have a symbol for C here. And what's Q? In terms of give that a couple seconds. Here I have a sigma here and a sigma here, and the sigmas could have been divided out, right? So I didn't bother to do that. Okay, so anyhow, there's our capacitance. We plug that in for the capacitance. For the charge, well, the charge is sigma A. We're getting short on time. So I'm going to just say, we've done the hard work here. I'm just going to say this equals, etc. You can fill in the etc. by simply using the expression we have for the capacitance. And it wouldn't hurt to use the expression with the sigmas here and here, but they'd still cancel out eventually. Okay, but obviously we just want to get them out right away. And what's the charge? Well, sigma A is equal to the charge, right? And sigma is E over 4 pi K. Okay. So we put all that together and we get an expression for the energy density of an electric field. And it doesn't apply just to fields between the plates of a parallel capacitor. If you know what the electric field is over some region of space, you integrate to get total energy using this idea. Okay. If you know the electric field, you know the energy density. And you get an expression, just a little simple out. You will see that expression, the final expression you get. Bring back control or bring back alternate tab, please, somebody. I can't navigate without it. Where is it? If you look at the chapter summary, you get it. Now it's okay. The formulas you see in the chapter summary are all in terms of epsilon naught instead of K. All right. We talked about that before, but let's be sure we say that. Pi k is 1 over epsilon naught is 1 over 4 pi k. And you see a formula where the energy density is 1/2 epsilon naught E squared. This will be expressed as sigma over epsilon naught without the 4 pi k. I prefer when introducing this stuff to use the 4 pi k because the 4 pi invokes the area, surface area of a sphere. And remember, we started talking about flux, if you remember, flux of a point charge Q through an enclosing sphere. Okay. And the surface area of the sphere is always 4 pi r squared. The field is k cubed over r squared. And thus you get your first form of Gauss's law, which generalizes to any surface enclosing a charge. A quick word on dielectric constants. You have good pictures in the chapter. Read the chapter and you won't understand. Let's just look at the effect of the dielectric. Okay, so you have charge density. Sigma again. So you got some plus charges on one side and some minus charges on the other. I kind of think I remember drawing this picture before, maybe not. Okay, and let's say you've got water in between the plates. Now that's not necessarily a good idea because water will have impurities, cause charge to flow and kind of kill your capacitor, okay? But let's say we did have water in some kind of a bag in here, okay? Some kind of insulator that allows the water molecules, which are, you got hydrogen and one oxygen and 2 hydrogen atoms. And essentially then these atoms become little dipoles. Okay, so instead of writing an atom with 3 charges on it, I'm just going to pretend you got an atom like this with a positive and a negative end. Okay, so this is what my atoms are going to look like, even though they're really hydrogen atoms with angle close to 120 degrees and all that stuff. Okay, so what's going to happen is the water molecules between here and here are going to align themselves with the electric field. So that the negative end is here. You can't see it. I've just written a negative, positive, negative, positive, negative, positive, negative, positive. The end result being that you have negative ends of the molecules here and positive ends here. So now it's as though you have a bunch of negative and positive charges opposing the positive and negative charges. The capacitor, which reduces the electric field. To the extent that in water, for every 80 charges over here, you get like 79 opposing charges from the polar water molecules. So this is just a picture. Dielectric reduces the electric field so reduces the voltage given charge since you reduce the voltage and the capacitance is Q over V, that increases the capacitance. It means for given voltage, okay, let's just say we're cranking that Wimshurst generator, okay? And we got a water bag in between the two plates. And somehow we've got to fix the charge doesn't leak and gap, okay? That means for a given charge that we put on those plates, we get much less potential difference. So for the same potential difference, we can put a lot more charge on. So it increases the capacitance, and commercial capacitors almost always have a dielectric, which is often just a thin film of some material that has polar properties analogous to those of water. Now, there are very few materials that do a better job than water, but water is not practical. So you put a film between these things and an insulated film. It allows you to move the plates much closer, which also reduces the voltage. It allows you to put much more charge on capacitor. Okay, well, we're out of time. We're right on time, that's unusual. So you need to do a little reading, okay? So, and I think the idea of dielectric is, I'm not sure that that's addressed in the transition problems, but it's not a difficult concept. Kappa is your dielectric constant. You can say something like C equals kappa times C naught, where C naught is the capacitance of an air capacitor. That is, the capacitor has air between these, or actually even a vacuum capacitor. That's really what you see now, because air has a small dielectric constant. There's a little bit of polarity involved there. It's like 0.1% or something like that. Okay. For C naught is your basic capacitance that you calculate without a dielectric. And I'll mention that kappa for water, I think, is around 80. And there's some material, I haven't looked at it, and I looked at it sometime in the last couple of years. You look at you just search the internet for dielectric constants, and Google or AI or something will give you a table. And there's one substance that had dielectric constant around 240, I thought. I could be remembering that wrong, but it's a few times higher, than water, which is around 8. Materials that are commonly used, I think, have dielectric constants that maybe go up to around 50 or 60. But that's a vague memory. I haven't looked it up recently. Interesting to look up once you understand what the dielectric constant is. Again, it's just you put a material in here so that something within the material orients itself with the electric field and reduces the electric field inside. Now, there are capacitors in parallel and series. We spent too much time talking about other stuff. We don't have time to talk. Don't have time to spend more than a day on the chapter, okay? Assuming the preparation of the transition problem. Parallel and series capacitors are pretty simple. I'll just say, if you got two capacitors in series, then you'll have a charge like plus Q here, minus Q here, plus Q here, and minus Q here. This is continuous conductor, so you can't have a net charge here. So whatever the charge here is, charge here. You compare this to capacitors in parallel. You have the same voltage across both of these capacitors. It's like you're sharing the surface of this one and the surface of this one. So it's like you have, let's just say that these were equal capacitors, you'd have twice as much surface area here. So you'd have twice the capacitance. Okay, so it's like you add capacitances if they're in parallel. If they're in series, the reciprocal capacitance is the sum of the reciprocal capacitances. So it's like here you have 1 over C of 1 over C1 plus 1 over C2. Like resistances, but this looks like parallel resistances. It's for series capacitances. Here you have C equals C1 plus C2, because you're essentially sharing the area. Here, you have just one potential across the whole thing. I'd have to draw more and explain it more. And I can do that if you really need me to, but read it. Because really next time I need it getting into the next topic. Okay. And try to be as well prepared as you can for the test. Because that's going to prepare you to understand the next chapter.